Okay, lecture 2. So in the previous lecture, we talked about how to start from the Hamilton equation of motion. And then you can study the classical Poisson bracket. And Dirac proposed that by quantizing, or by applying the so-called canonical quantization condition, you can convert classical mechanics to quantum mechanics. So the Dirac canonical quantization condition is Qi Pj is IH bar delta Ij. So again, delta Ij is defined as 1 or 0. If I is equal to j, then the delta function is 1. If I is not equal to j, then the delta function is 0. But the question is, what does Q really mean in quantum mechanics? What does P really mean in quantum mechanics? So the big picture here is that the physical reality that we try to describe is the actual quantum state. The quantum state can be denoted as n. And this symbol is called a ket. Okay, this symbol is also introduced by Dirac. And in order to obtain more information about the quantum state, we need to apply a so-called linear operator on this quantum state. So you will apply linear operator F on the quantum state. Then you can get either the so-called eigenvalue, or you can get the expectation value. If this quantum state is an eigenstate of this linear operator, then you will get an eigenvalue. The eigenvalue corresponds to the physical observable. That is what you can measure in the experiment. But of course, sometimes your quantum state is not an eigenstate. And then in this case, what you can calculate is the expectation value. All of this are actually telling you the information about the dynamic variable or dynamical observable. All right. So this is our big picture. But of course, I have several quick notes. The first note is the quantum state. The quantum state is really the physical reality. It's objective. And it can be studied by different ways. Or we can say it can be represented or described by, for instance, by wave function. You're all very familiar with wave function, cosine. But wave function is just one way to describe the quantum state. Although, yes, wave functions are usually used by chemists, but it's just one way, one of the many ways to describe the quantum state. We can also use matrix, right? A quantum state can be represented by a matrix, and the operator can also be written in a matrix form. This is also very popular in the actual calculations. Whenever you actually perform a molecular quantum mechanical calculation by using a program, the program is actually doing linear algebra. You can also use quantum number to describe the quantum state. Sometimes we're only interested in the quantum number. Or you can even use the summation of paths. Now, this approach, the summation of paths, is actually proposed by Feynman. This is the so-called path integral approach. We will not talk about this approach in this course, but I just want to remind you that this is an alternative way to describe the quantum state. So actually, this formalism, the path integral formalism, is quite popular in modern research when you study the chemical dynamics. It has a very close relation to the Lagrangian mechanics. Now, the second note I want to say is that about the dynamic variable. Dynamic variables are experimentally measurable. Okay, so in principle, you can measure the eigenvalues, but maybe it's not easy to actually design the experiment. But in principle, they are definitely observable. A measurement will, in general, alter the original quantum state. And this is a very important consequence of the measurement. Because after all, a measurement is really an interaction between your original quantum system and the environment. We will talk about the measurement a little bit more in this lecture. But let's first start by talking about the linear operator. Okay. What is a linear operator? Suppose you have two sets. Let's say you have set X you have set X, and you have another set Y. And you have several elements inside set X, and we can consider several elements inside set Y. Now, you can construct a map from set X to set Y. Depend on the nature of this map, you can have several different mathematical objects. If we consider set X is a number set, all the elements are numbers. And set Y is also a number set. All the elements are numbers. And then this map, of course, give you a function, f of x, right? If we only consider a single variable, but of course you can consider multiple variables. If you want to generalize this map a little bit, for instance, if we consider each element in set X to be a function or a matrix, and set Y is still a number set, then this map is called a functional. This is a functional. You can denote this as capital F, f of x, if we're talking about a function. So a functional is really a function of a function. So its variable is a function or a matrix. And you can map a function or a matrix to a number. So this is a functional. For instance, energy is a functional of the electron density. Electron density itself is also a function of the position of the electron. So we can call that we can have an energy functional. So more general, I think the most general way is, let's consider set X to be function set or matrix set. And set Y can also be a function set or a matrix set. In this case, this is definitely much more general because a function can include a number. If this function is a constant number, then this is a constant function, right? So this case 3 is much more general. And then we call this map. If you map a function to another function, or if you map a matrix to another matrix, or a function to a matrix, etc., then we call this as an operator. And we denote it as capital F with a hat on that. Okay, here we put a hat on the letter. This is an operator. This is an operator. Sometimes in the literature, people will simply skip this hat. They just write a capital letter. But depending on the context, you can know whether or not they mean an operator. So just a quick note. This operator sometimes can also be written as, simply by using a capital letter F. Or people like to use F and you put a short line under this letter, especially when people are using matrix to represent an operator. They like to use this notation. Or sometimes people use a bold-faced capital letter to represent an operator or a matrix. All right. Then what is a linear operator? Definition. If operator F times C1F1 plus C2F2, here C1, C2 are numbers, are constant. Here in general, we can talk about complex number. Of course, if you only care about real number, they can be real number. But in general, C1, C2 are complex numbers. And F1, F2 are two functions. If you apply this F operator on this linear combination of F1 and F2, you get C1 times F on F1 plus C2 times F on F2. If you can linearly distribute this operator to F1 and to F2, then this operator F is a linear operator. Okay, this is actually a pretty straightforward definition because you see the F has this linear property. But one thing I think I need to emphasize here is that after you apply the F operator, you still get C1 and C2. You do not get C1, the complex conjugate. You do not get C1 star. You do not get C2 star. You still get C1 and C2. This is very important because in general, C1 and C2 are complex numbers. If you get C1 star, if you get the complex conjugate, then F is not the linear operator. So in a sense, the complex conjugate itself is not a linear operator. Okay, let's see several examples. Let's consider, for instance, the first order differentiation, partial x. Is this a linear operator? Of course, right? Obviously, ddx C1 F1 plus C2 F2 is equal to C1 times, well, here C1 and C2 are constant. So this is equal to C1 times partial x F1 plus C2 partial x F2. Of course, this is a linear operator. Or let's consider this operator as simply a function, g of x. This is a simple function. Is a simple function or a simple constant, a simple number, are they linear operators? Yes, they are linear operators, right? So actually a function or even a number, a constant, can also be considered as a special case of linear operator. Let's consider the gradient operator. The gradient operator is defined as here, Ex, Ey, and Ez are the three unit vectors along the x, y, and z axis. So the gradient operator is really a vector, right? If you apply the gradient operator on a scalar function, you will get a vector. So is this gradient operator a linear operator? Of course. Because this gradient operator is a linear combination of three first order differentiations, right? And first order differentiation, or actually even a second order or even higher order, are definitely linear operators. So a linear combination of the linear operator give you linear operator. How about integration? Yes, integration is also a linear operator, right? how about the complex conjugate? So as I mentioned previously, a complex conjugate is not a linear operator. C1F plus C1F1 plus C2F2. Complex conjugate, or if you really want to write it in a sort of operator way, so you write F. F means the complex conjugate. So this will give you C1 star F1 plus C2 star F2, which is actually equal to C1 star F1 star plus C2 star F2 star. This is just a notation. We want to write it in a more a formal way by using an operator. But as you can see, we after applying this operator, what we have in general is C1 star or C2 star. And in general, C1 star is not equal to C1. C2 star is not equal to C2 unless C1 and C2 are real function, are real constant, right? Unless C1 and C2 are real constant. So in general, complex conjugate is not a linear operator. How about sine function? Is sine function a linear operator? It's not, right? Because sine C1F1 plus C2F2 is certainly not equal to C1 times sine F1 plus C2 times sine F2. In general, you will not get C1 sine F1 plus C2 sine F2. Therefore, sine is not a linear operator, right? How about square root? Square root is not, in general, a linear operator. How about log or natural log? They are, in general, not linear operator. All right. So we have talked about the concept of a linear operator. Then we need to talk about the simple algebra about the linear operator. Let's see several definitions. Summation. You can define the summation of operator A and operator B. And the summation means the summation of operator A and B means you first apply operator A on F, then you apply operator B on F, then you add them up. This is pretty straightforward. You can define multiplication. A times B. A times B means you first apply operator B on F. Operator B on F, then you will get a new function. And then you apply operator A on this new function. This is the definition of the multiplication. Just a very quick note. In general, A times B is not equal to B times A. Unlike we multiply two numbers, if you multiply two numbers, A and B, of course, AB is equal to BA. But for operators, they do not commute. We say this is not commutative. Okay? We will talk about several examples about this. It turns out, this fact is very, very important in quantum mechanics. It gives you the uncertainty principle. Okay. we can also define a so-called identity operator, or sometimes called unit operator. Capital I and with a hat. I means identity. The identity operator is like number 1 in multiplication. Identity operator times any function gives you the function itself. So in this case, we can also define the inverse of an operator. So if A times B is equal to B times A is equal to the identity operator, then we can say B is the inverse operator of A, and you can denote B as A to the -1 power. Okay, A to the -1. Okay, this is simple definition. Okay, let's see several examples. Let's see the first example. Let's do gradient operator times gradient operator. What do you get? Well, you get EX times partial x plus EY times partial y plus EZ times partial z, and you multiply this term again. And of course, you see the 3 unit vectors EX, EY, EZ are orthogonal to each other, which means EX times EY or EX times EZ or EY times EZ is 0. And because they are unit vectors, so EX times EX is 1. EY times EY is 1. EZ times EZ is 1. And therefore, you end up with, well, partial x times partial x, you get second order differentiation. Partial squared, partial x squared, plus partial squared, partial y squared, plus partial squared, partial z squared. So this, we can denote this as del squared. This is called the Laplacian operator. Very common, it's very common in quantum mechanics. So here, we have used the fact that d times d, or d squared, is partial x times partial x gives you the second order differentiation, partial squared, partial x squared. Okay. Let's see example 2. Let's consider operator A as a single function, x. Let's consider operator B as ddx, or partial x. Now, what is the commutator AB? The quantum bracket, or the commutator, is defined as AB minus BA, right? Then, if you apply this on any function, that's just in general, right, f of x, if we just consider the one-dimensional case, since both the operator A and B are one-dimensional. So let's just use a one-dimensional function, f of x. And based on our definition of the product of A and B, we have A times, you first apply B on f of x, minus B times you first apply A on f of x, right? So what do we get? we get x times partial x f minus partial x. Well, actually, if it's just one-dimensional, we can use ddx, but here I just use this partial derivative. X times f of x. So the first term is very straightforward. It's just x times df dx, right? Minus the second term is, please pay attention to here, you have a function here, and you are doing a first order derivative. So what you have is minus f minus x times df dx, right? You have two terms, not just one term, you have two terms. And therefore this is equal to negative f of x. So you see, an operator times a function gives you another operator. As I said previously, a constant can also be understood as an operator times a function, right? Or a function or a number can also be understood as an operator. So that means AB minus BA is equal to -1. Or another way to write this is AB minus BA is equal to negative identity operator, right? You can write 1 or you can use identity operator. Both are fine, right? 1 times any function gives you this function. If you want to write in an operator form, then you can write 1 as an identity operator. Okay. So this is a very important property here. So x, so here we have x and ddx. They do not commute. And what is this commutator? The value of this commutator is equal to -1. All right. Now, if we consider, say, Q1 as x, operator Q1 as x, which means the position of the first particle along the x dimension, then let's consider P1, let's consider another operator to be a constant times partial x. K is a constant. In general, a constant in quantum mechanics is a complex number, okay? So, of course, now x is just a, right? We have talked about this a here. And this p operator is just k times b, right? Okay, now let's see what is Q1, P1. What is this commutator? Now, in our first lecture, we said the quantum operator is simply IH bar times the classical Poisson bracket. And we know that there are several very simple algebraic properties you can use for your derivation about the classical Poisson bracket. And since the quantum bracket is simply a constant times the classical Poisson bracket, so inherently, all the quantum commutators naturally inherit the algebraic property of all the classical Poisson bracket, right? So all the algebraic property of classical Poisson bracket can also be applied to the quantum operator, to the quantum commutator, right? All right. So I will not repeat this simple algebraic properties. So Q1, P1 is now equal to A, because Q1 is equal to A, P1 is equal to K times B. So this is equal to, using the algebraic property, this is equal to K times AB plus AK times B, right? Okay. So this is K times AB plus, what is AK? A is simply X, right? A is simply X, and this is a number. K is also a number. Of course, X times K is XK minus KX, and this is, of course, 0, right? Because they are all very simple numbers. So the second term is 0. You will get, and we know AB is this commutator, AB minus BA is equal to -1, and therefore this term is equal to -K, right? And Dirac told us what? Dirac told us Q1, P1 should be equal to IH bar, right? Notice that here I'm talking about 1 and 1. So I is equal to J, the delta function is 1. Q1, P1 is equal to IH bar. In other words, the position and its corresponding conjugate momentum do not commute. And the result of this commutator is IH bar, right? This is what we have learned in the first lecture. Now, that means here Q1, P1 is -K. And Dirac told us Q1, P1 is IH bar. And that means K must be equal to -IH bar, right? Therefore, what is the momentum operator here? The momentum operator of 1 should be equal to -IH bar ddx, right? P1 is K times B. K is -IH bar. B is ddx. Naturally, P is -IH bar ddx. And actually, here we don't need to use 1. We can just use X, because we're considering Q1, actually it's QX, which is the position of X. This operator is simply X itself, right? These two operators are extremely important. We consider position X and its conjugate momentum Px. The operator for X is simply the function itself, X. The operator for Px is -IH bar ddx. Okay? So this can be generalized to other dimension. For instance, Py is -IH bar ddy. Y is just Y. Pz and the V operator is simply V. Okay? This is very important. Okay. And this, but let's see. How did we get Px equal to this? Because based on the fact that we let X or Q1 to be simply the function X, we can derive this expression for Px, right? So actually we let X simply is X, right? the operator of the position self is simply the function self. And this is called the position representation. This is actually very common for molecular quantum mechanics. And a chemist usually likes to use this position representation. Chemists usually like to use this position representation. Okay. But you will say, what if we let Px simply as Px? The momentum operator simply be equal to the momentum itself. Then correspondingly, what is the X operator? Then X is not going to be equal to X, because otherwise you will not have this commutator IH bar, right? So if we let Px be equal to simply the momentum function itself, then what is the operator form for X? Because X Px must be equal to IH bar, right? This is what we learned from Dirac. Dirac told us because of this one-to-one correspondence between classical Poisson bracket and the quantum bracket, or the quantum commutator, you must have this property. That means actually X is equal to IH bar partial Px. Why is that? Well, this is equal to X times Px, right? IH bar partial Px times Px, right? Minus Px times IH bar ddPx. So here I no longer write out a general function f, unlike here I write a f. This is actually very helpful if you are a beginner, right? You just need to pay attention here. The second term actually contains two terms here, not just one. But once you are familiar with the algebra of the operators, you do not need to write a general function, okay? So you just directly do summation or the product of the operators, but you just need to be more careful, okay? You always think about a general function is always here. A general function f is always here, but you don't need to write them out, okay? Okay, so this is what? The first term is simply IH bar, dpx is 1, right? So the first term is simply IH bar. The second term is what? The second term contains two terms, right? Plus IH bar px dpx minus IH bar px partial px, right? And this is equal to IH bar. So as you can see here, this commutator xpx is still equal to IH bar. However, x in this case is equal to IH bar ddpx, right? This is based on the assumption that we let the momentum operator simply be equal to the momentum function itself. And this is called momentum representation. So in the position representation, x simply is the x function itself, and the px is negative IH bar ddx. But in the momentum representation, px is simply px function itself, and x becomes positive IH bar ddpx. The coordinate representation, or the position, this is also called a coordinate representation. the position representation is very commonly used in chemistry, and a momentum representation is commonly used in describing the structure of the solids. If you talk about the band structure, you need to talk about the K space, the momentum space. In that case, it's more easier to use the momentum representation. All right, so for the majority of this course, we will use the position representation. But of course, in several lectures, we will talk about, for instance, we talk about the free particle, or talk about electrons under a periodic potential. We talk about the solid state structure. Then we will switch back to momentum representation. All right. So next, I need to talk about a very important concept, eigenvalues and eigenfunctions. Okay, let's first see the definition. If you apply operator A on a function, you get a constant times a function. Again, a constant in general is a complex number. Then we say A, when we say the function f is the eigenfunction or eigenstate of the operator A. And this small a is called eigenvalue. Okay, this is a very straightforward definition. Actually, this is consistent with what you have learned in linear algebra. If A is a matrix times another matrix, you get a constant times another matrix. Then this matrix F is simply the eigenvector, right? Let's see several examples. Example 1. Let's consider f of x is exponential ikx. And let's consider px operator as negative IH bar ddx, because here we only consider only the x dimension, so we can use ddx. But in general, you can consider multiple dimensions, right? Because here you have the three components of the momentum px, py, and pz. You can add them up to get the total momentum operator, which is a vector actually, right? And of course, you can also get the momentum squared, which is connected to the kinetic energy, and the momentum squared is a scalar vector, I should say. No, sorry, I should say it's a scalar operator. All right. So of course, based on what we have learned in lecture 1, you already know that this represents a plane wave. Well, it's not a traveling wave because it does not contain the time-dependent term, but still it's a plane wave because you can write this function as a combination of cosine and sine using the Euler function. So it will represent a plane wave. Here, k of course is the magnitude of the wave vector. The wave vector is the magnitude of the wave vector times a unit vector along x direction, right? All right. So let's see what is the eigenvalue. So you apply px operator on the function f of x. You get negative IH bar ddx times exponential ikx. And this is equal to negative IH bar times ik e ikx. And this is equal to I times I is -1, so this is equal to kh bar EIKX, right? So operator times a function, you get a constant times the function again, right? So what do we get? So the eigenvalue is, we can write the eigenvalue as Px is Kh bar. So the eigenequation is Px operator times the function is equal to the eigenvalue times the function. So eigenvalue is Px, Px is Kh bar, right? That means, okay, the momentum of this plane wave is actually Kh bar. And because K is equal to 2 pi over lambda, we know Px is K times h bar, K is 2 pi over lambda times h bar. And h bar is, again, it's the original Planck constant divided by 2 pi, we get h over lambda. The momentum is equal to h over lambda, right? This is the famous de Broglie wave, right? Lambda is h over px. Okay. This is, of course, the de Broglie wave. You see, everything becomes very clear now, right? This is what motivates us to write the momentum operator in this form, right? Here is a simple example to demonstrate this point.